Oh, yeah, here we go into integration by substitution, often known as U-substitution. Let's dive into this thing. So basically, the whole idea here is that we can manipulate integrands, this part, to fit our older integration ability. So I call it more manipulation to set up integration. Before, you manipulated by changing exponents from negative to positive or square roots into exponents. Now we're going to get a little more involved into manipulating the integrand so we can integrate it. So the instructions are integrate and check your solution. And the big things to note here is that it looks like the chain rule has been here. So you've got this function within a function, and then you've got a derivative of this inner function right here, 3x squared, or something a lot like the derivative. That's the sign that U-substitution is the way to go. So the number one thing you look for is that you've got a function within a function. That's like 95% of the time that's going to be your U value, maybe 90%. So I'm going to let U, check this out, I'm just going to let an arbitrary U value equal to the innermost function. That's x to the third plus 1. Now from there, we now need to substitute everything in this expression that's in terms of x. Now we need to rewrite it in terms of U. No x can be left behind. Okay, so what do I do to do that? Well, first thing is we notice we have a dx, and the only way to get that is by taking the derivative of this. So I've got du dx is equal to, that's just the derivative, of 3x squared. What I'm now going to do is solve for du. You're going to multiply both sides by dx. So you get du equals 3x squared dx. And I say multiply because technically we're not doing that, but in the grand scheme of calculus, we don't need to know the whole proof just to be able to rock U-sub. So now you've got du equals 3x squared dx. Now what do I do with that? Well, we see that that is exactly what's right there. So we now substitute. In for x cubed plus 1 goes u equals x cubed plus 1. So that's just u. You still have the cube there, so this has become u. This right here has become du. That whole thing is exactly what it is. Now that everything is in terms of u, there's no x's left behind, we integrate with respect to u. Normal integration, so it's going to be u to the fourth all over 4 plus c. Not bad. And now, last but not least, we put everything back in terms of x. So what is u? U is equal to x cubed plus 1. So you get x cubed plus 1 all raised to the fourth all over 4 plus c. That's it. That's your answer, which is pretty cool. Now, the really neat part is when you check this over, right? So let's do the check. We take a derivative like we always do, and if we derive it correctly, and we did our integration correctly, we'll end up with our original integrand. So the derivative of all this, the 4 comes out front, so you get 4 times x cubed plus 1 all over 4, don't forget about the chain rule, times the derivative of the inside, which is 3x squared. Oh, look at that! The 4's divide out, and you're left with exactly what we started with. Of course, the plus c went to 0. Seeing this, we now see why the U-substitution method is often known as, or what I call, reverse chain rule. Right? It's undoing that chain rule. So if you notice a chain rule has been there, or you notice there's a derivative that has popped out of something, right? Or you've got a function within a function, often U-substitution is the way to go. All right, let's do 2 more examples in this video. Let's go with these 2. So integration by substitution is going to work here because look, you've got a function within a function. And if I take the derivative of this, we'll get something with an x. Right, and here's something with an x. So I'm going to let u equal the innermost function. Now, if you were to pick the wrong u value, you'll know pretty quickly because you'll have a lot of x's left behind, or maybe the integrand gets messier, then just start over and pick another u value. So u equals 10x squared minus 4. I'm going to solve for the derivative, go right for it, du equals 20x, derivative of minus 4 is 0, dx. That's me combining the step of du per dx, and then multiplying it over. So that's it. So these are our substitution pieces. Now, u equals 10x squared minus 4. Okay, so that's going to be u to the fourth. Now, this one's interesting. du equals 20x. I don't have a 20x in here. I have an x, right? And I've got this 3, by the way, which I'm going to pull out of here. You've got an x dx. How do you make 20x dx? Well, I could multiply this by 20. So what I'm going to do, check this out. I'm going to, and I guess I'll erase this to show you this step right here. What I'm going to do is I'm going to put in the 20. I'm just going to magically put that 20 in there. So 20x, and then you've got your u to the fourth dx. Now you have your x dx. I've put in the 20, making this a perfect substitution. But I can't just multiply by 20. I'd have to also divide by 20 at the same time, or multiply by 1/20th. By doing that, we're multiplying the whole thing by 1, but notice I'm getting the du that I needed. So that leaves me with 3/20ths on the outside. 20x dx becomes du. Nice. Then you get u to the fourth. Again, you multiply through by whatever number you need to make this term, the dx term, exactly equal to du. And whatever you multiply by, you've got to divide out by that same number. Otherwise, you're changing the value of the integral. Okay, so from here, we just integrate like normal. I get 3/20ths chillin' times u to the fifth over 5. The integration's very, very nice. Plus c. And now we plug back in. Well, that's going to be 3 over 100, a weird number indeed, times u to the fifth. That's this to the fifth. Nice. So it's 10x squared minus 4 to the fifth plus c. There we go. And you can put the 3/100ths over without the dot, but that works. All right. I encourage you certainly to check your solution. We'll do that real quick. If I check my solution, I'm going to get 3/100ths. Chain rule, 5 comes out front. And then we've got everything to the fourth. That's looking good so far. Times the derivative of the inside, which is going to be 20x. Ah, look what happens. 5 times 20 is 100. They cross out with the 100 down there, and you're left with 3 times 10x squared minus 4 to the fourth x, which is exactly what that was. Oh, it's beautiful. It's beautiful. All right, last but not least, your innermost function is often going to be your u value. No difference here. So we're going to let u equal to 9t, right? That's the inner function in here. So we take the derivative. Du is equal to 9. In this case, it'll be dt. Look at that. We have the exact 9 dt. It won't always work out perfectly like that, but when it does, sweet. So this is equal to du. We get the integral, the indefinite integral of sine of what is now u. Not u, but u, the letter. Du, because 9 dt is du. Now you integrate like normal. The integral of sine of u is minus cosine of u plus c. And we substitute back in u for for t, which is 9t, plus c. There you have it. And of course, we'll do our answer check. So the derivative of minus cosine, well, the derivative, we get that minus 1 from minus cosine times minus sine, that's the derivative of the outside, times the derivative of the inside, which is 9. And the derivative of c is 0. Negative times a negative, a positive, and you get back to your original integrand. That's it. If you happen to notice this problem, you're like, wait a second, I know that the derivative of that inner is going to give me the 9. Some of you will be able to do this mentally and without U-substitution. If you can do that, go for it. Listen to that inner voice and do it without the U-sub. So that's it. My first little video on U-substitution. We'll continue with more U-substitution examples, just kind of spreading out all the different kinds of examples you could see in the next video. I'll see you there. Peace.